Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on February 2nd, 2026, just about 8 days ago. It introduces a new optimizer called MSign that prevents training instability by periodically restoring the stable rank of weight matrices, essentially ensuring the model maintains a high effective dimension during learning, and it achieves this with less than a 7% computational overhead. The paper is titled MSign, an optimizer preventing training instability in large language models via stable rank restoration. And as we'll see later, the results are really impressive, showing that this method prevents collapse in models where standard optimizers fail. Figure 1 illustrates the two key warning signs that appear right before a model crashes. In the top chart, the gray line tracks the gradient norm, while the colored lines show the stable rank. Notice that around step 20,000, the stable rank drops sharply, and immediately the gradient norm explodes, shooting up by orders of magnitude. The bottom chart reveals the second culprit, Jacobian alignment, shown in blue. This metric rises at the exact same time, confirming that collapsing rank and high alignment between layers work together to drive the instability. Well, Figure 1 identified the warning signs, and now Figure 2 proves they directly drive the explosion. The blue line plots the theoretical lower bound for the Jacobian norm, derived from the stable rank and alignment metrics. Beneath it, the gray line tracks the actual gradient norm observed during the run. The key takeaway is how tightly they couple. As the theoretical bound rises around step 20,000, the actual gradients immediately surge, confirming that the mathematical model accurately predicts the crash. Alright, moving to the main results, Figure 3 demonstrates that MSign effectively prevents training collapse across every model scale tested. The top row tracks training loss, where the blue lines for the standard AtomW optimizer consistently fail, showing sudden spikes in models ranging from NanoGPT 5 million to Llama Mixture of Experts 3 billion. In contrast, the orange lines for MSign remain stable throughout. The bottom row explains why this happens. While the baseline gradient norms explode exponentially, MSign keeps them bounded, successfully breaking the feedback loop that leads to instability. While Figure 3 demonstrated stability, Table 1 now assesses the computational cost by comparing training throughput in tokens per second. Theoretically, the overhead should be negligible, often less than 0.1%, as shown in the bottom row. However, in practice, implementation factors like distributed communication add some real-world latency. For larger models like Llama 1B and Llama MOE 3B, the measured overhead sits between roughly 4 and 7%, which is still a modest trade-off for preventing failure. So, having established the throughput in Table 1, Table 2 now pinpoints exactly which layers require this intervention. The authors run an ablation study on NanoGPT-5M and Sigma-40M to see where MSign is most effective. Crucially, the bottom row shows that applying the optimizer only to the MLP layers fails to stop the crash, resulting in the same outcome as the standard AtomW baseline. This proves that the attention layers are the primary driver of instability. While treating attention layers alone stabilizes the run, applying the method to all 2D parameters consistently yields the best perplexity scores. Okay, Table 2 showed where to apply the optimizer. Table 3 now asks how often, testing the application period P. The first column lists periods ranging from every 10 steps up to 100,000. The results reveal a clear trade-off. In the top row, applying MSign every 10 steps drags throughput down to roughly 18,000 tokens per second. On the other extreme, waiting 100,000 steps is too long, causing the model to fail. The authors identify the sweet spot around P equals 100, which restores throughput to over 24,000 while keeping the training stable. Wrapping up, two takeaways stand out. Training instability in large models is driven by measurable mathematical collapses rather than random noise. By periodically restoring stable rank, MSign offers a robust, low-overhead solution that could make training massive architectures significantly more reliable. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.